So let's now consider boundary conditions. And I'm going to begin with region 2 first because the boundary condition here is a little bit more intuitive. So region 2, or it's a little simpler when you think about it. So let's look here at region 2. So here is my general solution. Now if you look at these solutions for my wave function, one of these two solutions actually can run me into a lot of trouble. And if you think about it a little bit, you might become suspicious that it's this solution, right? Because as x goes out towards infinity in region 2, right, and that certainly is a set of locations contained in region 2, as x goes out to infinity in region 2, this would make my wave function blow up and become infinite out at infinite distance. That sounds kind of disturbing. It's even more disturbing when you realize, well, that function is going to be very hard to normalize. We won't be able to find the integral of psi squared, right? Psi squared would also be exponentially increasing, and so we won't be able to normalize it. We can also think of kind of a physical reason why that might be difficult. If I imagined, say, my system like so, here's x, right? Here is like my step in my potential, right? My little step here. And maybe I'm doing some experiments, and here is my laboratory, right? And if I look at my wave function, it's growing exponentially, right? So also if I look at the probability of x, it will be growing exponentially, right? And it can get quite large. In fact, if we really think about it, if you want to think about the universe, right, it's got a finite size. So I might go all the way out here, say, to the edge of my universe. And if I were to do that, you see I'm going to get a tremendous integral under this growing exponential. So to make sure that it integrates just to 1, what that means is I'm going to have to divide it by this very large number. So the final probability distribution will look something like this. It'll be 0 everywhere, right? And it'll just be at the very edge of the universe, this exponentially growing peak, right? And what this situation describes then is not a particle in my laboratory and not a particle anywhere near my step. I'm describing a particle that's off at the edge of the universe, and that is not my situation. So I can rule out this type of situation. So this then leads us then to our first general lesson on boundary conditions. So this is a lesson, and we're going to put a box around this. This is boundary condition type number 1. It's just as a general statement, our wave function, I should better call it phi, right? Our wave function, phi, as x goes to either plus or minus infinity, right, can't blow up on me. So it has to approach or not approach as I go out there, either plus or minus infinity, right? This is one of these, not allowed symbols. We can't have that situation happening. So that's a general boundary condition we can apply under all conditions. The same argument would apply to the time-independent Schrödinger equation. And one of the key things that teaches us then is that for us, we can narrow down the solution in region 2 then to not contain the growing exponential, but to only contain that decaying exponential part. So it will have just this one particular piece of the solution, and it won't have any D2. So it will look just like this. And you may be wondering, okay, I still have one undetermined parameter here, but that parameter you see ultimately just sets the scale of phi. And that parameter will be determined. We will determine it later. It's related to the normalization of the overall wave function. So we really have done a good job and solved pretty much everything we would want to solve for region 2. We've got our wave function there up to a normalization constant. Now, one last comment I wanted to make was that in this type of a region, if the region extends out to infinity, just as a tip to you guys, I generally find form 1 more convenient for this reason, that then it is much easier to apply this particular type of boundary condition. Very good. So that's the boundary conditions for region 2. We still have to attach this now somehow to what's going on in region 1, which has these two adjustable parameters. So we have to find a way to connect, really, what is going on in region 2 to what is going on in region 1. So there's really another region we need to talk about that we haven't discussed much in depth, and that is this transition region here.